Hello, this is the next video in a playlist that I'm calling Correlation, and we're going to talk about partial correlation. And in this video we're really going to just talk about the general concept of partial correlation, and then in follow-up videos we will discuss and derive formulas and prove certain properties, but this is meant to be a general overview of the concept of partial correlation. Now, it was developed by Carl Pearson in 1896, and it measures the correlation between two variables while controlling for a set of other variables. Okay, so first, nomenclature. A zero-order correlation is, and it'll be denoted by row 1, 2, is just the correlation between the first and second variables, in your data set. And it's Pearson's correlation, sometimes what it's called zero-order correlation. Now, one order or first order correlation, denoted by row of 1, 2, dot 3, is a correlation between variables 1 and 2, that's the 1, 2, while controlling for variable 3, that's the dot 3. And it's first order because we're controlling for 1. And notice here it's zero order because we're not controlling for any. It's just a simple correlation between the two variables. And just to make sure that we drive this point home, a second order correlation would be denoted by row of 1, 2, dot 3, 4. And this is equal to the correlation between variables 1 and 2 while controlling for variables 3 and 4. And so to generalize, it could be the kth order correlation. So it'd be denoted by row of 1, 2, dot, and then there's k variables here. It's a correlation between variables 1 and 2 while controlling for variables, 3 through however many you have, k other variables. So now for formulas, now several different formulas exist, in which they're all equal. They're all fine. Some are easier to compute, some are harder to compute, but this video is just a general concept. Later videos will display the formulas and prove all them. So the basic idea is this. So how to compute row of xy dot z. So this is, we want to find the correlation between variables x and y, and we're controlling for this set of variables. So there's p different variables that we're controlling for in this correlation. So the concept or the goal is to remove the effects of z, so all these variables from x. So remove the effects. And to do that, you regress x onto z, and then we calculate the residuals. And we'll follow up with this in a second. So then we want to remove, step 2 is we want to remove the effects of the z variables from y, and to do that we regress y onto z and then calculate the residuals e of y. So now we have two sets of data, ex and ey, and now we calculate the zero order correlation between the residuals from x and the residuals from y, which is the partial correlation between x and y while controlling for z, and it's denoted by this. So let's examine these steps in a little more detail. Okay, and I'm going to reference some ideas and concepts from videos that I have in a playlist, General Linear Models Regression, where we have 70 videos starting from the very beginning and then going up to as difficult as you need to go. So here we want to, so in step 1 we want to regress, we want to remove the effects of z. So that means regress x onto z. So that's what we do here. So x is the dependent variable and the z's are the independent variables. Okay. So now when we do this, and the theory behind it, there's what's called a hat matrix. And it's the design matrix Z. So it's Z, Z prime, Z inverse, Z prime. And this is called the hat matrix in multiple regression. And again, I have some videos in this playlist, untitled hat matrix. So which would be, if you're unfamiliar with that term, it'd be good there. Now, this is the big important concept. If we pre-multiply a vector by h, okay, so we have a vector in space and we pre-multiply it by h, then this projects that vector into the column space of z, so which we'll denote by c of z. So there's a vector out there dangling. We pre-multiply by h and it projects it down into this column space of z. Okay. Now pre-multiplying a vector by I minus h projects it into or onto the orthogonal complement space of z, which is we'll denote by c of z complement. So they're perpendicular to each other, these spaces are. So then we take the predicted values. Remember, we want to find the residuals. So the predicted values, which we call x hat, we obtain from the hat matrix times the x vector, right? Because it projects it down into the column space of z, which is then our predicted values. So to calculate the residuals, we take our data minus the predicted values, and then those are the residuals. But if we plug in what the predicted value is, we can right factor out an x. Okay, so then we have I minus h x. So this is the residuals, and notice that it's onto the orthogonal complement space of the z's, of the, of our data matrix. And that is hugely important, which we'll see in a second. Now we do the same thing for y. We regress y onto z, and then notice that the independent variables are the same, so the hat matrix is going to be the same. This is a perpendicular projection matrix onto the column space of z. So to find the predicted values, we pre-multiply y by h, and then that gets us a vector of predicted values that actually live in the column space of z. Now to calculate the residuals, we'll call it EY. We take our data y and minus the residuals, and then if we replace what y hat is, we can right factor out a y. So we're pre-multiplying y by I minus h, which then projects this y vector onto the orthogonal complement space of the column space, of z. Okay, so now here is the crux of this concept. So the residuals, EX, is the information for X that is orthogonal, which means independent in this statistical world, of Z. So we've extracted all the information of X that's independent of Z. And that's what's in here. And that's what we want. We don't want Z interfering with our correlation between X and Y. So we've taken X and then removed the effects of Z. And that's what this E of X is. And E of Y is the same thing. It's the information for Y that is orthogonal, which means independent, of Z. Now these two, this is essentially X with Z removed. This is essentially Y with Z removed. Now we just take the simple correlation between them. So, which is this. So we have a vector of numbers and a vector of numbers, and then this is the, this ends up being the zero order correlation between these two residual vectors. But that it equals this. And so see video in this playlist that I call Geometrical Interpretation of Pearson's Correlation Coefficient. But what this is, from page 1, this row of xy dot z measures the correlation between x and y while controlling for the variable z. Okay, and that's the basic concept of what partial correlation is. And in the next few videos, we're going to follow it up with some formulas and properties that will, be more mathy about and prove. Well, I hope you enjoyed this video. I sure did. Please like it and subscribe so you don't miss the next one. Thanks. Bye.